Good afternoon, ladies and gentlemen. I think we'll get started, even though it's only 5 after. Welcome to another in a series of seminars in the I for Energy Center series. My name is Gary Baldwin. I am the Director of Special Projects for Energy and the Environment at CITRIS, and would like to thank the CIE, the Center for the California Institute, there's so many centers, the California Institute for Energy and the Environment for sponsoring the lunch and as a co-sponsor for this event. Hello to our web viewers, especially our CITRIS sister campuses at UC Davis, UC Merced, and UC Santa Cruz, and anyone else out there looking at us on the web. In addition to the lunches that you picked up on the back table, I would like to draw your attention to the flyers that are there which announce the other talks in this seminar series. We will go throughout the semester every Friday. Some of the talks will be in this room, and when this room is not available, we will go back downstairs to room 250 in Sudarjadai Hall. I would also like to announce and remind folks that on October the 20th at 4 p.m. in this room, we will have a distinguished speaker, Chang-Yu Huang, former CTO and CEO and president of Samsung Electronics. I hope you will be able to join us. Today we are honored and privileged to have Professor Cyrus Wadia, the co-director of the Clean Tech to Market Center at the Haas School of Business, with us talking about low-cost photovoltaic technology using metal sulfides. Cyrus currently holds a dual appointment as that co-director and a guest scientist at the Lawrence Berkeley National Laboratory. He spent the last 6 years at Berkeley and LBNL in pursuit of new low-cost photovoltaic technologies using earth-abundant metal sulfides. He was recently honored by MIT as one of the recipients of the Technology Review 35 Award. He did his doctoral studies. Prior to his doctoral studies, he was in Silicon Valley launching a series of new technology companies, not the least of which is the company Avanco, and more recently a co-founder or founder of the boutique internet service startup specializing in complex data analyses, and now serves as chairman of the board there. Cyrus did earn his PhD in energy and resources, the ERG group from here at UC Berkeley, and holds both an MS and SB in chemical engineering from MIT. Cyrus, thank you very much for joining us today. Let us welcome Cyrus Wadia, please.
Thank you. Thank you, Gary. Okay. So, the title of this talk is a bit ambitious, Solar Energy for 7 billion people. And the core of my work is this notion that our ability to solve big problems with technology may not be limited by our imagination, but rather by our resources. And hopefully I'll give you a flavor for what that really means as we walk through this conversation today. And to start off with, try imagining for a moment scaling a particular technology to 7 billion people. And everybody, potentially in this room and outside of this room, online, has their pet reason for wanting to do this with unsubsidized solar energy. But I can't today point to any existing technology in the market that can actually do this. So what I'm going to try to do is give you a little bit of background for how I think about approaching this problem, launch into how existing technologies may be limited, and talk directly about some new approaches that we've been taking here at UC Berkeley and Lawrence Berkeley Lab, namely my work with copper sulfide and iron sulfide. So when I think of scale, and scale at the magnitude we're talking about, 6-7 billion people on the planet, I don't think about how do we get more solar on the rooftops here in Berkeley. I view this as how do we actually get solar to folks in villages like this. Now, 20% of the world population, that's over 1 billion people today, have no access to electricity. And this is an image of a village I visited in China, in the Yunnan province. We're about 3 hours away from any paved road. They're earning probably around $300 a year. And you could probably look at their conditions and say they're better off than some in the world, but they're probably worse off than most. And the reason I went to this village and a few other surrounding villages in China was so that I could personally better align the technology that I'm developing with what their needs are. And when I think about like I said earlier, the pet reasons for solar could range from climate change to energy security. But when I think about poverty, I feel like we have a huge opportunity to use electricity to pull folks out of impoverished conditions like this. And this is the backdrop for the talk, because when we open up the question, how do we scale to 7 billion people, I think this is where you need to start, what you might call the lowest common denominator. So let's start with some real core principles here. There's cost and scale. And cost, naturally, we need to hit a price point that someone who earns only $300 a year could actually afford. Again, I'm talking solely about unsubsidized solar electricity. Now, scale is a trickier one because, again, it's unlikely that any one technology could scale to meet the needs of 7 billion people. But if we looked at solar today, every solar panel that we have the ability to manufacture today, that means all the cumulative capacity that was built over the last several decades, if we manufacture that today, it would cover the size of Berkeley. And to give you a sense of how much energy this is, it basically would satisfy the needs of New York City on a hot summer day. Actually, it would satisfy 50% of the needs of New York City on a hot summer day. So roughly around 6 gigawatts. Now, the area is interesting to me because if you think about silicon being used as the dominant source for solar, stop for a moment and compare silicon in solar cells to silicons in microprocessors. So, a standard wafer, I'm not sure what the state of the art is, but it might be 300 millimeters. And if we use that 300 millimeter wafer, we can get roughly 500 microprocessors out of that. That would feed 500 computers. So think about the benefit of that. Now, that same 300 millimeter wafer of silicon, if it was converted into a highly efficient solar cell, would give you 14 watts of energy. And that's barely enough to power, well, certainly an incandescent light bulb in your own home, but maybe it would power one compact fluorescent. So I give you this analogy because I want you to have an appreciation that as we think about solar serving the needs of this many people, we are going to be putting so much strain on our resources in a way that we've never done before to get, the type of scale is going to be challenging. Now, one more point on scale to bring this into perspective. This is a chart that shows total worldwide electricity demand, and it's growing steadily over time. And it shows a slice, this maroon slice, is photovoltaics. And I draw this out 10 years to show that even if photovoltaics, the industry today, it's growing at about 40 to 50%, and it would be phenomenal if we could expect that type of growth rate every year for 10 years. But let's say we did. Let's say we were successful at achieving that. We still would only accomplish 2.6% of the market. So again, I'm trying to frame this in a way that we're solving this problem, but maybe not everybody working on solar is solving the same type of problem or in a time frame that's really meaningful. So let's start talking a little bit more about what solar looks like today. Now, this number is a key number. If you were to walk into any solar manufacturer today, this would be on their whiteboard. They'd be discussed in their boardroom. It's $1 a watt. And for many years, this was the mythical price point at which everything would be better. So $1 a watt, I want to dissect that a little bit. But to do that, I want to bring up a term called grid parity. And this is a chart I borrowed from a colleague at Signet Solar. And it's a fairly busy chart, but I'm going to try to explain these piece by piece. So what you have here are 3 different axes. This axis represents power price for households, ranging from 2 to 38 cents per kilowatt hour. And you can notice that different geographies have different power rates. China would be low, very cheap energy. Netherlands, Denmark fall pretty high. On this axis, this is an axis representative of how much insolation is in that geographic area. So you should think about this side of the chart as sunny, and this side of the chart not so sunny. And so you can see, India, Texas, California here, Norway, Sweden, Finland here. Now these curves, these isoquants represent what the actual levelized cost of electricity would be if you sold solar at $8 a watt installed, $6 a watt installed, for so on and so forth. And by plotting this, you can actually get a sense of what you need to get to be grid parity. So if I walk into the boardroom at SunPower and they're focused on $1 a watt for the module, right, installed, they may still be, even if they achieve $1 a watt for the module, they may still be somewhere in this region where they're, in a non-subsidized way, competitive in Hawaii, Italy, and our Tier 4, Tier 5 pricing here in California. So what I look at is I say, well, in an installed sense, we need to be somewhere between $2 and $4 a watt installed. But let's say we got there. We still leave off the two biggest markets we're concerned with, China and India. As I said earlier, this idea of scaling to 7 billion people, we want to start there. So let's talk about where we are today. Now, a total installed system, traditional system in the market today is about $8 a watt. And I break this down with the cost to refine and process your silicon, to encapsulate it into a module that, plus adds another $2.18 per watt. The inverter, this is the installation, and there's a labor piece to that, and then this big number here, pardon me, is certification and the built-in profit for the solar company. So all of this sums up to about $8 a watt. This is where we are today, and we just said that to be competitive in a non-subsidized way here, we need to be somewhere between $2 and $4 a watt. But another thing you might appreciate is if I gave you the silicon for free, fully processed, or if I even gave you the entire module for free, let's say it costs $0 per watt, you're still saddled with more than $4 a watt in the balance of systems. And so this is an area that we need to appreciate, that it's one thing to attack the top of the food chain here and say, as I will later today in this discussion, that we need to look at different materials, but the different materials we look at need to be processed in a completely different way so that in some sense we can change how we think about the entire installed cost. So once again, at $8 a watt, if this was a home here in Berkeley, for your typical home household load, you would be looking at something around $30,000 today. And let's say they can get down to $5 a watt, so they've shaved a few dollars on the module, they've shaved a few dollars on the balance of system. So now you're looking at about $18,000. It's a little bit more palatable, but still not quite unsubsidized electricity here. So for us to be unsubsidized here, we're looking at a system for your home around $7,500. But to actually get to that price point that makes sense for these folks in these villages, we're looking at install costs around $200, and that's 75 cents a watt, and that's taken directly from that grid parity chart I showed earlier. So it's a difficult problem to think about, but we've sort of laid a groundwork for thinking about fast enough and cheap enough, and now I want to introduce the incumbent players and talk a little bit more about them. So for most of you, you're familiar with pictures like this. This is the picture of the future. This is a picture of how solar is going to be installed in these massive arrays in the desert. And for many, it's a very exciting picture. For me, I think about things in a very different way. Reaching folks out in these villages in China, I want to be thinking about distributed energy, not relying on large installations to bring my overall cost down. So this is pretty much where the industry has been heading. And to give you an appreciation of the costs involved, specifically with silicon, I want to take you through the process of getting silicon from sand, which is where we start, to an actual finished module. Now, silicon starts with silicon dioxide, which is quartz or sand, and the first step to actually break that silicon-oxygen bond is this step right here, what we call reduction. We use an arc furnace to reduce that, and it has a fairly high energy input, 24 kilowatt hours per kilogram. Just to give you an order of magnitude comparison, if you were to do the same separation with an iron oxide, trying to separate the iron from the oxygen in a standard iron oxide compound, that number would be more like 2 kilowatt hours per kilogram. So out of the gate, silicon is actually quite high. But that's not even where we want to begin, because that gives us about a price point of $1 or $2 per kilogram, but that's metallurgical grade silicon, and we can't make solar cells out of metallurgical grade silicon yet. People are working on different ways of isolating impurities, but I'm just talking about the traditional industry, what you could buy more or less off the shelf today. So then you go through this complicated Siemens process, which adds, ultimately, to get to the purity levels you want, it adds, goes up to $25 a kilogram. So about an order of magnitude change from metallurgical grade to this pure grade. Now, the question you might ask is, why so pure? Well, with silicon, this is all determined by the physics of the material. So silicon has what we would call a very poor absorption property or absorption coefficient, meaning we need a very thick material relative to other semiconductors to absorb the same amount of energy. Now, when you make it thicker, what you're adding is a longer pathway for your electrons to move out of the device. And when you do that, you have to ensure that you have a very pure bulk material. Otherwise, your electrons will get lost. So as you grow a film in this direction of thickness, you have to increase the purity to compensate for that. This is one of the hurdles for silicon. The other side of that problem is, when you make it thicker, now you're dealing with a more rigid form factor, and you may have less flexibility in terms of knocking down some of the cost components I was talking about earlier with the modular encapsulation or the balance of systems. So that's silicon. But then in comes thin films, and thin films are a really exciting new development in the solar industry, because basically two technologies, CAD-TEL and SIGs, they've found a way to use less material and process it faster. They, in fact, have come down to about $1 a watt in module cost, and that's CAD-TEL, that's First Solar specifically. I just talked to a fellow at First Solar yesterday, and he says that they actually are down to about $2 a watt in balance of systems. So now we're down to $3 a watt, a tremendous leap from that $8 a watt that we're reporting on just last year. So we've solved it, right? We've got $3 a watt for residential installation. Surely they'll drive that cost down over time. And then for a distributed DC solution, maybe out in China, you can imagine a $2 a watt solution coming down over time as well, close to that 75 cents a watt. But there is one Achilles heel to all of these materials, and that is the actual composition of these thin films depend on very rare and scarce compounds. We have tellurium, indium, gallium, and selenium. And so when we look back at this question, can we scale to 7 billion people, and we take that analogy with the silicon wafer that I gave earlier, now you have an appreciation, well, how far can we get with these? Surely we're going to penetrate the markets in the near term, and as the market stays small, there's always going to be a place for these, but what happens when we try to get to terawatt hours? Is there enough? So we tried to answer this question, and we did an analysis that looked at the raw material abundance of natural elements like sulfur and tellurium and iron and others, and we matched that with the physics of semiconductors. So we looked at the actual band gap of the materials, the absorption properties of the materials, and we said, okay, best case scenario, if we dug up all the iron or selenium in the ground or cadmium, how much solar can we roll out? Let's just get sort of the limits and then kind of work off of that. So in doing that, we produced a chart that looks like this, where we have 27 semiconducting compounds on the x-axis, and the y-axis is a logarithmic scale. We have annual electricity production, and in terawatt hours. So these are really big numbers, and to sort of ground your eye, this line right here coming across is total U.S. consumption at 4,000 terawatt hours, and this line right here is worldwide consumption at 17,000 terawatt hours. So at first blush, you look at this and say, okay, well, there's an ordering where some materials look really good and some materials maybe less so. But when you take a closer look, the ones that fall on this side of the chart happen to be the candidates for these new thin films at low cost. So this isn't really a discussion on whether we should be producing these or not. We're very excited because by their work, we're going to learn new things about processing and distribution of solar panels. But when we looked at this, we said there's some unusual candidates that seem to have gotten missed. In 30 years of solar research and development. And this is where we decided to focus our attention. So we were looking at iron sulfide, copper sulfide, and so on and so forth. So now I'd like to turn your attention for just a brief discussion on research and development. Because this story has sort of evolved into how do we better leverage basic science R&D to satisfy these large scaling type questions. And it's important to know the history of where we have been with solar. So this is a chart that looks at the last 30 years of basic science R&D, federal from the US, into solar. And these are different solar. This is photovoltaics, which is primarily what I'm talking about, but then you have solar thermoelectric, solar heating, and look what happens. In the late 70s, we had this enormous spike, and then in the early 80s, administrations change, objectives and priorities change, and we're back down to a very low number. This is, in 2003 dollars, only roughly between $100 and $200 million. So one way to think about the impact of our federal R&D on basic science is to think about where the technologies have sort of tracked in that same time period. So this looks at, over the same time period, what we view as the most important benchmark for solar cells, and that's efficiency. Or we have viewed it as that. And what you'll see is we look at different types of technologies from crystalline, polycrystalline, to SIGs, CdTe, amorphous, and you can see that there are these long sort of progress curves where we go from low efficiencies to slightly better efficiencies over time. But you can see that the path is long. It has taken a while for us to actually get higher lab efficiencies, not quite at the rate which we had expected. But when I go back to this spike in PV funding here in the late 70s, what I notice is that really the interesting science work happens at the tail. So where these tails start really matters. And for the better part of 20 years, we didn't have really any new investment dollars in new technologies for solar. So we maintained this progress on existing technologies, but it wasn't until really in the mid-90s that things started to change, because it wasn't viewed really as solar work here. This is all new polymer and nanochemistry work, but it grew into more or less a solar project. So the point I'm trying to make is, because of that spike and then the downturn, we lost some momentum. And there's a close correlation then between what we invest in and kind of what we can produce and what the output of our labs at the university and national labs are going to be. So I'd like to take you through that the red thread just in a little bit more detail and give you a little bit more background on the field of science that I'm working in. So back in 1986, our field was given birth. It was a 1% all polymer organic photovoltaic cell. And this was a really exciting development, because it said, look, we can see photovoltaic properties from materials that are not semiconductors that have the ability to scale, that could be produced cheaply, and thus started a thread of work on all of these polymer, or what we call organic solar cells. Now, in the lab that I've been fortunate enough to be part of, in basically 1996, they published a paper where they said, well, what if we took out one of the polymers and replaced it with a semiconducting nanoparticle? Wouldn't that actually produce more photocurrent or a better charge mobility than in just the all polymer? And what you see is some very modest efficiencies, 0.5%, which kind of paled in comparison to the 1 to 2% that they were already achieving in all polymers. So this group, the group that I've been part of, worked then mostly on shape control of these nanoparticles. So they said, look, okay, maybe we don't get a great efficiency right now, but that's because we have these dots, these spheres. Maybe what we should do is actually work on synthesizing actual natural percolation networks in our material so that the chemistry solves the efficiency problems. And so that went on for many years, and still today, we didn't really get very far on what I'd call a hybrid thread. We got to maybe about 2%, but there there's certainly some issues there. So more recently, these hybrid devices were combined with nanowires, but another thread that actually occurred again in our lab was an all-inorganic nanoparticle solar cell. So basically said, forget the polymer altogether, that's become a limit. Why don't we take all the polymer out and just use nanoparticles? And my colleague Alon was working with CAD-CEL and CAD-TEL. Okay, so the reason I give you this background, there are a few other more recent advances, but I want to key in on this. The reason I give you this background is when I joined this research group, I looked at that and I said, this is a promising platform that we can build on, but CAD-CEL and CAD-TEL, I'll tell you right now, won't scale to the levels that I care about. So what if we could actually use some of this knowledge and build on development of new materials, or what we call abundant materials. So to kind of summarize, again, I view these as the tails. The tails are where the interesting science happens. And some of this is more mature on the organic side. There's still tons to be done there, but this is the thread that I'm going to talk about next. So I go back to this chart and I said, okay, well, clearly we've missed some opportunity to work on materials like this. Some groups had in the late 70s, but that pretty much evaporated in the 80s and 90s. So let's go back to that. Let's see if we can build on this platform, this nanocomposite platform that I just discussed, and let's get a little bit deeper onto those materials. So the next thing I did is look at cost, because I said scale and cost both matter here. So this is scatter plot where we index all the materials I'm looking at to crystalline silicon. And in a traditional McKinsey-style chart, you want to be in the upper right-hand quadrant. And this is basically iron sulfide, completely off the chart. And then there's a cluster of these other compounds, and then you can kind of see where your favorite semiconductor might sit. But I looked at this and I said, okay, yeah, iron sulfide and copper sulfide both meet the scale and the cost concerns that we're talking about. But how about performance? Because that matters as well. This is a chart that some of you may be familiar with called the Shockley-Quasar limit. And this is looking at band gap energy versus theoretical power conversion efficiency. So a semiconductor basically is going to be limited thermodynamically by the band gap in terms of how efficient we can be for a single junction solar cell. And that's what this curve represents. So the materials that fall at the top of that chart, the bar chart, are all north of 25%, similar to silicon or gallium arsenide or CAD-TEL, the materials that you're used to in the market today. So not only are they abundant and very cheap, but they would perform equally well. So the story started getting a little bit better. The last performance metric I'll show you is this idea of absorption length and diffusion length. And this is maybe a little bit more than what you bargained for today, but I'm going to basically just draw your eye to two things. Silicon is up here, and iron sulfide is down here. So when you compare silicon to iron sulfide, there's a vast difference in terms of how thick a material you need to absorb the same amount of energy, several orders of magnitude. So remember what I was saying before with silicon, one of the hurdles is that because we go thicker, we need to be more pure. Well, iron sulfide, we can do it at 20 nanometers, the same that you would do with silicon on the micron scale. And at 20 nanometers, that opens up a whole new possible door for processing, controlling self-assembled nanoparticles. You can do a lot more, but you can also worry less about the defects on the iron sulfide because the pathway for the electrons is so short. Okay, so now I want to turn your attention to the chemistry that we did and give you a little bit of background on that. So when you start looking at these materials, you run into basically the puzzle of our project, which is phase purity. And when I say phase purity, I'm talking about the actual composition of the material. So copper sulfide, I listed here as CuXSY, comes in many different flavors. And you can kind of, and this is just a partial list. So you can see that historically, copper sulfide has been hard to synthesize and isolate the exact compound that you want. This is what we want. It's called chalcocite, Cu2S. And chalcocite has the optimal band gap for what we want to do. But if I made you some chalcocite with a trace amount of something else, I'm going to kill all the photovoltaic properties of my material, because the band gap, like I said, determines how good you'll do, and you're limited by basically your weakest link. So if I have any phase impurity, I'm not going to actually be able to achieve the result I want. Iron sulfide has even a more complicated issue. It has this same issue with many phases, but FeS2 is the one we want, yet there are two flavors of FeS2. There's pyrite, which is the desired band gap, and then there's marcasite, which is undesired. So if I trace back to 1978 through about 1985, there's a group in Germany that was working on iron sulfide solar cells, and they were trying to do, in many ways, what we were doing, or what we are doing. And they had very modest efficiencies, and a lot of kind of how they try to explain that is that in their synthetic approach, they were not able to isolate the pure phase of pyrite. They had this impurity marcasite. So we look at that as, again, an opportunity for nanoparticles. So this is sort of the what is nano slide. Many of you may be familiar, but just to give you sort of a concept of how big we're talking, this structure is 100,000 nanometers wide. This is a strand of hair, and this is 1,000 nanometers wide, and this is basically a red blood cell. So now you're looking at this and saying, nano is very small. I get that. Going back to my cost and scale argument for solving this problem, nanotech actually is also at the junction of where cost and scale meet, because we can process things in a completely new way, solutions-based processing of nanoparticles, and this is actually what led us to look at nanoparticles of copper sulfide and iron sulfide. When you combine this with the actual purity question, we thought we had a way. And I'll say one more word about the phase purity. Because we're working on such a small scale, it affords us an opportunity to actually synthesize things from the ground up that are more pure. And this is sort of a common characteristic of nanochemistry, that you are able to make more pure semiconducting nanoparticles because it's energetically unfavorable for impurities or phase impurities to actually be incorporated in the lattice. So working small works really well, and actually in some ways might help us scale big. So now for a little bit of background on the chemistry that we went through. This is a typical apparatus in the lab. This is called a colloidal synthesis, a three-neck flash synthesis, where we basically, it's like cooking. We throw a bunch of stuff in the pot, we heat it out, we agitate it, we run it at atmospheric pressure. We might flow an inert gas over it. We might, ramp the temperature differently. But really, the magic is in what we put in the bottom here. And at least it has been for our syntheses. And for us, we were very fortunate to come across, or to actually develop, a new form of synthesizing copper sulfide, and the phase that we were interested in, this chalcocite. This is a TEM image, transmission electron microscope image, of our copper sulfide particles. And in nanochemistry talks, we love to talk about how pretty our pictures are, and this is considered a nice picture. I'll show you a picture that's not so nice of my iron sulfide later, but these are 5 nanometer particles, and they're monodispersed, and they pack like ping pong balls would. And from there, we can actually lay down a film of this and see if we can make a solar cell. A few more points on the results of this work. Some of you may be familiar with X-ray diffraction. It's a way to actually understand what your crystal structure is. For me, it's a way to know if I have any impurities. And again, when we started this project, we didn't find many or any really papers that could isolate pure chalcocite. And so this is a very good sign, because this represents, these red lines represent where the peaks should be in this diffraction pattern, and the black represents where our particles are. And again, it's just another, corroborates the fact that we have very pure material, one that's well suited for a solar cell. This last chart here is called an absorption spectra, where we can try to understand where the band gap is. And the copper sulfide has a very sort of traditional indirect band gap feel on the absorption, so it has this sort of long, steady rise. And when we kind of extrapolate where it rises, we see that the band gap is 1.2 to 1.3, which is right in the ballpark of what we would expect. So in order to go from that synthesis to an actual device, we take our material, and after some cleaning steps, first of all, this is copper sulfide, a vial of my copper sulfide, and this is a vial of my CAD sulfide with an associated transmission electron microscope picture. What we do then is we take these liquids and we sequentially deposit them on a conductive glass substrate. So that's what this is. We put down some copper sulfide, low temperature anneal it, about 150 degrees for 5 minutes. Then we put down CAD sulfide on top of that, same, do a small anneal, and then these are our contacts. So each one of these are thermally evaporated, and the end result is a chip that looks like this. It's 1 square inch, very small, and each of those pads, those aluminum pads, represents an individual solar cell. So when we test it, we have 8 solar cells that we can cycle through very quickly. But this is basically how we're doing our work. Now, this is the standard IV curve to talk about how efficient your solar cell is. Pardon me. And I'll just talk about these numbers. Our open circuit voltage, 0.6 volts, is actually quite a good number. It's what we would have expected for the band gaps we were working in. This is the number that concerns me, the 5.6 milliamps per centimeter squared. It's very low, and as a result, we have this, modest efficiency, 1.6%. Now, the 1.6% again is, I call it a platform because this is sort of the first proof of concept of this architecture. So naturally, it's going to take time, hopefully not too much time, to actually figure out how to scale this and scale it at a higher efficiency. But these are chemistry and physics problems. There's no earth abundance problem here. It's just how quickly can we put the right minds to figure out how do we get from 1.6 to maybe north of 10%. But we're very happy with this result. One other thing that I show here is called the external quantum efficiency. And the other thing I'm going to point out here is copper sulfide absorbs to about 1,000 nanometers. But here we see a sharp drop-off after 700 nanometers. And this is probably due to some intermediate defect state that's introduced when copper diffuses from copper sulfide into cadmium sulfide. It's a known issue with bulk semiconductor copper sulfide and CAD sulfide. We don't know yet at what rate ours are sort of subject to this. But when I saw this, I kind of recognized that and thought, at least this is a problem that we can identify and figure out how to solve immediately. And then from there, we can kind of work upwards of 1.6%. The last thing I'll say about the copper sulfide device is this is a picture of me in the lab torquing the actual plastic substrate it's on. Because we were running at such a low temperature, we were able to deposit on plastic, and i.e. a flexible substrate, and show that the current doesn't change as a result of torquing it and trying to break it. This is a new result because to date, the only other all-inorganic nanoparticle solar cell had to be deposited on glass because they ran at very high temperatures and very harsh conditions. So this, again, points towards this direction of, can we process things in a slightly different way, in a way that could scale more broadly? Okay.
Excuse me, you told us how you put down the copper sulfide, but where did the CAD sulfide come in?
So the CAD sulfide is there to create the...
No, I know that, but you have this procedure.
Yeah.
Where is the CAD sulfide in this procedure?
We do another synthesis of CAD sulfide, so separate, not shown, and then we clean it and we pull it in vials like this, and then we use that after the copper sulfide is laid down, we deposit the CAD sulfide on top of that. So it's a sequential deposition. Now, the last material I want to talk about before wrapping up is iron sulfide, and that many of you have heard about as called fool's gold. And that's what it looks like. Some of you may have touched this or played with this as kids in your rock collection. But for us, what I was saying earlier, this issue of are we making pyrite or marcasite was really the key question. So we came up with a recipe for developing pyrite in a very different way. We were doing these in what's called an autoclave. So it's like a pressure cooker. You put a bunch of ingredients in, you seal it, you heat it up, and then it reacts under high temperature and high pressure. For us, it's not that high. It's 200 degrees, about 200 psi. But I like this reaction because it's in some ways very elegant. It's a molecular precursor that we synthesize, that's this right here, and combining it with a co-surfactant, CTAB, and water, and we put it into this sealed vessel, we let it go, we produce these large blocky nanoparticles of iron sulfide. And these iron sulfide blocks are very large. They, remember the copper sulfide was about 5 nanometers, so I had this very nice material I could just spin down on substrate. These are much bigger. These are, 200 to 500 nanometers. So, one of the issues I've run into in making devices is how do we actually deposit these on a substrate, because they don't pack quite as nice as those small particles. Well, to bring you back to an X-ray diffraction pattern, which we talked about earlier as a way of knowing the crystal structure, this basically represents, again, the red lines are where the peak should be for a pure pyrite sample, and this is our sample. So we believe we have one of the first very pure synthetic pathways for producing phase pure pyrite. And that's an exciting development because that's, in some ways, a harder problem for us to get the phase exactly where we want it. Now we're working on figuring out ways to either grow those smaller or to actually deposit them in a film and test the electrical properties. That's sort of next on the list. So I'll just give you a few concluding remarks, and then we can open it up for questions. So the first point is the primary two criteria for pervasive adoption, where we made the case for being cheap, being fast. I think we also made the case that today we're not equipped to deliver 17,000 terawatt hours of electricity in a meaningful time frame. And that's really what we're struggling with here. Silicon might be limited by cost and form factor. Thin films may be limited by material abundance in the long term at terawatt hours. And we haven't really seen a major push for new basic science in this field in many, many years. Now that's changing. It's changing as we speak. So not too soon, I guess. But new approaches are critical, and we have reason to believe that nanoscale photovoltaics of these earth-abundant material systems could provide this pathway. And we've demonstrated the first working prototype with copper sulfide, and we're on track for iron sulfide. So lastly, there's so many people to thank that I can't list them all by name, but a lot of the funding for this work came from the EPA and Lawrence Berkeley Lab and the Department of Energy. And with that, I'd like to thank you for your attention, and
Thank you.
there's some questions.
Thank you very much, Cyrus. I think we have lots of time for some questions, and so let's start back here. I'm going to hand the mic around, and maybe I can get a colleague to help me with another microphone.
So you're at 1.6%. When does it become, when can you imagine it becoming competitive with the existing PV technologies?
Okay, so if I'm right about cost and about taking a lot of the cost out of the processing and the balance of systems, I see it somewhere between 5 and 10% serving niche markets, potentially the ones I started the talk with.
What about, at scale, at current scale? When can it compete at current, with other technologies that are already at the current scale?
So, well, you got to ask which market you're referring to. So if we're talking about grid-tied markets here in the U.S., I think you'll have trouble at any percentage lower than 12%. And that's just because your incumbents all are there and better. And, here, the area isn't as big a constraint in some parts of the country, but it is in most of the parts of the country. So efficiency does matter.
Just one more follow-up question. So if you're talking about PV for 7 billion people, and you're talking about you have to be 12%, I'm sorry.
So if you're talking about gross scale, and you're talking about competing against existing technologies, what's the theoretical efficiency that's possible? Because 12% sounds kind of high, given the chart that you were talking about earlier.
12% is quite low. The theoretical limit for these materials is north of 25%.
Okay, thanks. I'm going to sneak in two questions if I can possibly do it. I've seen a lot of examples of cadmium sulfide quantum dots used as a way to enhance the photoreceptivity of other materials. Is that kind of the theory that you're using in this system? And number two, if you're going to talk about non-grid compliant power, which I think a lot of the world would be happy with, then do you really need inverters and AC? In other words, I'm looking at a philosophy there in terms of how you see power distributed at a low cost. If you can answer both those.
Good. So to answer your first question, no. The way we're using the cadmium sulfide is a transport layer for electrons. And the second question, I agree 100% on that, which is if we have a way of knocking pieces out of that BOS, then the inverter might be the first to go. You use DC to power a DC appliance or DC lighting or TV. Absolutely. So the more we can pull out, the better for this sort of longer term view.
Rough cost first for that?
No, I don't. Yeah.
I wonder if I could just bring up some physics issues, and that has to do with the material quality and material perfection that is desirable for solar cells. If you look at silicon, it is kind of an amazing material that it has very, very few defects. And apparently this is connected with the crystal structure, the rigidity, and so forth. And this is sort of not so much the creation of material scientists, but really it's something that God gave us. Silicon tends to be very, very pure, even if you're not that careful. Now, the purity is really kind of important, but in a way that's not brought up very often. It's much easier, for example, to think about the ability to collect current. You say, oh, if it's not pure, I can't collect the current because I'll hit a recombination center. But there's another way in which purity is very, very important, and that's the voltage. But the voltage part is very hard to explain, because then you have to get deeply into thermodynamics and try to understand it. But basically, the indication that your material might not be pure enough is when you see you're not getting the voltage that you ought to be getting. And that's a very strong indication. And it's also a very serious indication, because if it's impure and it stays impure forever, then you'll never get the voltage and you'll never be competitive, because you're not competing against coal-fired plants. You're actually competing against the 100 other different solar technologies that are out there. So you look at something made up of nanoparticles, and you say, well, what is an impurity? An impurity is even the surface. So if you have nanoparticles, you've automatically tied one arm behind your back because you have created something with a huge surface area. The entire surface is like one giant impurity, unless you're very careful with it. It sort of pushes you in a certain direction. I would say it pushes us toward materials that are sort of favored by nature to have extraordinarily high impurities, extraordinarily high purity. And the way we can tell is when you get close to the theoretical voltage. Now, the example you gave of 0.6 of a volt, the theoretical voltage should have been around 0.9 of a volt. So you still have a chance of collecting current, but will you ever break the barrier in getting the kind of voltage that you need? And so then you have to ask yourself, is there any hope of purifying these materials? Well, in nature, there are not that many materials that are really pure, and it seems like nature purifies them automatically. And the sulfides are kind of famous for not being in that category. The sulfides, as you showed us, have all sorts of valences. They don't know where they stand in terms of valence, and these are not the materials that nature has looked favorably upon. What do you do about this? I have a suggestion, is to work with materials that are inherently easier to purify.
Well, I mean, look, so that's basically historical. If you look at historically what we've done in PV, that's exactly what we did. We looked at high efficiency potential materials that, as you say, have this ability to be pure. You were right on all counts, your discussion about the voltage and the issue with sulfides. And I wish I had a better answer for you. I view nanoparticles as a way around that, but I know we introduced new problems. Namely what you said, not so much about impurities at the surface, but more about surface states being recombination centers. So I would be challenged to actually say that, hey, we can get to the 25% theoretical limit, but if we could get to a low efficiency, somewhere between 5 and 10, with these crude ways of doing things, then maybe we can start serving a market other than our own here, so a low power market. But to answer your question, what do? We put more scientists to work on this because there has to be a solution in there. I'm not willing to just throw it out completely because it's a difficult problem, but I understand how difficult it is. So thank you for the comment.
This could be the sulfides are not the right choice.
Right, and so we've also promoted the oxides and the phosphides, and there are problems with all of those, but there are several scientists here that are picking up the oxide work and potentially.
Let's take two more, one here and then one there.
Okay, I'm Lawrence Manuel, and you were talking about what the bulk of the system being, say, DC for small microgrids, but in the long run, you want to have many devices, and therefore you're really going to have an AC, and you're really going to have smart microgrids because of the conservation thing. So I would say that it needs to be integrated with high frequency, say on the 10 kilohertz or higher, just because the transformers are just too large for 50 and 60 hertz. And then one can see getting down to the 10 or 20 cents per watt range for smart microwaves, which would be very highly competitive and integrate with the types of systems you're saying.
Okay.
Yes, thank you. You originally framed this as promoting residential use, or that's what I saw in the shacks or the huts. Do you have any commercial imaginary for this or not? Thanks.
Well, if I were to sort of project into the future where this could go, I would first hope that we could use it in this distributed way for, pardon me, a distributed way for household use off-grid, and view that really as the beachhead for this technology to develop, because then you've already moved it past the lab scale into some sort of development, and if that's our beachhead sort of market, 2 billion people, that's not a bad place to start. And when we learn more about the system in a commercially manufactured way, then potentially we can move more upstream into markets that we're familiar with here. So.
Thank you very much, Cyrus. We can't fault you for being ambitious.
Terrific. Thank you.